The paper is ranking-aware unbiased post-click conversion rate estimation via AUC optimization on entire exposure space.
Hello, everyone. My name is Yu Liu. This work is by Huawei and Nanjing University. It's my pleasure to present our work on ranking-aware click conversion rate estimation via AUC optimization on entire exposure space. Let's start from an example of online shopping to illustrate the problem setting. There's a user who wants to buy pants and shoes, and once he clicks on them, he will buy them. However, he may not click on these items due to carelessness or some unattractive ads. So these items may not be clicked. Those items belong to a conversion set. The user actually clicks on the pants and the t-shirt. Therefore, these items are clicked samples. Ultimately, the only item the user buys is pants at the intersection of click set and conversion set. We can now formalize our description of the CVR estimation problem. This is a machine learning task where we wish to train a model outputs the probability that the sample belongs to the conversion set. In this problem, the input we need is all exposure samples with their respective conversion labels. But in fact, we can only get the clicked samples with conversion labels and the unclicked samples with conversion labels. Since only clicked labels have conversion labels, that can be directly used to train to the model. We face two important issues in CVR prediction problem: data sparsity and selection bias. In classical scenarios, only a few items will actually be clicked, and even smaller fraction of these clicked items will result in conversions. As a result, samples for training the CVR estimation models are very sparse. This can lead to high variance in training and thus insufficient model capacity. Statistically, unclicked items are not randomly lost and may have a higher CVR, and clicked data do not necessarily have a higher CVR. Therefore, the data distribution in click space is different from that in the entire space due to the effective of user's selection bias. Therefore, if we train the model directly in the click space without the bias, the optimal solution obtained is likely to be only a suboptimal solution for the entire exposure space. To address data sparsity, we need to fully utilize the unclicked samples to enrich the dataset and thus reduce the variance. To solve the selection bias, we need to use an unbiased objective function to obtain our unbiased estimators. Numerous researchers have made great efforts to address the data sparsity and the selection bias challenges in CVR estimation. There are two mainstream methods, which we call sequence-based methods and carol-based methods. Sequence-based methods, such as ESMM, deal with data sparsity by treating CVR as an intermediate variable derived from CT-CVR and CTR. So they can train the CVR estimator over the entire exposure space. However, this approach still suffers from bias. Carroll-based methods such as multi-IPW can deal with selection bias by eliminating the influence of input features on CTR task and obtain conditionally unbiased estimates of CVR. However, on the CVR in the click space can be estimated or implicitly the CVR in the entire space. Through the investigation from previous methods, we found that there encounter a trade-off. Training a model over the entire space often means biased CVR estimation. On the other hand, unbiased estimations of CVR is provided. It's often not possible to explicitly train on the entire space. Here, we use a new technology called AUC optimization to solve both the problems. AUC optimization is a machine learning paradigm that aims to maximize AUC by minimizing the AUC risk. In order to understand AUC risk, it's necessary to mention other definition of AUC. It's the probability that the model scores a positive sample higher than that it scores a negative samples when samples are randomly selected. The purpose of AUC risk is to penalize pairs of samples in which the positive sample scores are lower than the negative sample scores. Putting AUC optimization in the context of the CVR estimation task, we need to minimize the AUC risk of treating the conversion set as a positive samples and the non-conversion set as a negative samples. However, since only labels of clicked samples are available, they suffer from data sparsity and selection bias. Here's a new question. Can we use properties of AUC optimization to minimize the true risk across the space with a limited number of labeled samples? Now let's get into our proposed methods. Entire-space weighted AUC, EWAUC for short. Our framework takes all the samples in entire space as input and trains two towers with shared embeddings. The first tower is CTR tower. It can naturally train with clicked and non-clicked samples. Here we use cross-entropy loss for its training. The second tower is CVR tower. To solve the problems of data sparsity and selection bias, we use designed AUC loss to train. I will introduce the designed AUC loss. We train CVR tower by minimizing this loss. The AUC risk computed on the click space and the AUC risk computed on the entire space. For the AUC risk computed on the click space, we reweighted it with the inverse of the PCTR. As long as the PCTR estimations is accurate, then we can debias this in click space. For the AUC risk computed on the entire space, we treat the entire set of all samples as conversion and non-conversion samples separately, while weighting the samples in the click set too. In this way, we allow the model learn the distribution of samples across the entire space and reduce the variance. We have carried out a theoretical analysis of proposed method and obtained the theorem not shown. Our method train on the model train on the entire space, and the resulting estimator is unbiased. That is, minimizing our EWAUC risk, we can maximize the AUC of the estimator over the entire space. In addition, we conducted an empirical analysis. The results obtained in real-world datasets and as can be seen from the table, our EWAUC is more stable and performs better than other methods. We also conducted an application study. We compared EWAUC with two weekend versions, WAUC that uses only the clicked data, and EWAUC that is not reweighted. The results of WAUC have higher variance. This may be due to the fact that WAUC was trained using a smaller amount of data. The EWAUC shows lower AUC metrics, revealing the negative impact of selection bias. To summarize, the CVR estimation faces two challenges. One is data sparsity, which leads to high variance, and the other is selection bias, which leads to target inconsistency. Our proposed EWAUC method solves the data sparsity problem and the selection bias problem. In conclusion, EWAUC outperforms other methods, both theory and practice. Thank you for listening.
Thank you for your presentation. So we are a little late, but we have time for one question. Questions from the audience? Okay, I have just a curiosity about your model, whether it is possible to use it for different kinds of conversion. For example, when the last step is purchasing an item or listen to a song or watching a video. Or it is domain dependent?
We are working, let me show, that we use the dataset of online shopping. And we set AP test on our ads platform, and it has some likely 3% CVR increase.
Okay. Okay, thank you again.
Thank you.
So,